Welcome, everyone, to today's Explainer. I am absolutely thrilled you're joining me, because today we are looking at one of the most highly critical, absolutely foundational processes in the entire world of industrial construction. We're talking about the first alignment in rotating equipment installation. If you've ever wondered how these massive industrial plants operate so smoothly day in and day out, well, the secret lies right here in this exact procedure. I mean, think about it for a second. We are talking about colossal pumps and motors spinning at thousands of revolutions per minute. What prevents these massive machines from literally vibrating themselves to pieces? For any beginners stepping into the world of mechanical engineering or plant construction, this is the ultimate hook. Without the incredibly precise step of first alignment, the immense kinetic energy of that heavy machinery would simply destroy the equipment. It's literally a battle against microscopic deviations to save tons of steel.
Okay, let's dive into our roadmap for today. We'll start with the core philosophy of alignment. Move into Phase 1 on the shaft. Check out the alignment toolkit, explore Phase 2 for the DBC check, uncover the hidden dangers of a soft foot in Phase 3, and finally, look at the specialized millwright skill. Let's get into it.
Section 1. The core of alignment, setting the centerline. To kick things off, we really need to establish the macro-level stakes here. Why is first alignment treated with such reverence in the field? Well, according to our source material, it is the single most important and time-consuming activity in rotating equipment installation. Getting this right is what guarantees the machine's performance and its entire lifespan. If the alignment is off even a tiny bit, it generates immediate destructive vibration. And here is a golden rule for the field. This first alignment absolutely must be done before the final coupling and the suction or discharge pipes are connected. If you connect those pipes first, their weight might actually pull the machine right out of alignment.
Section 2. Phase 1. Shaft alignment.
So in industry jargon, the shaft is the central rotating rod of the pump or motor. Our main goal here is to ensure both shafts share the exact same geometric centerline. But there's a geometry we're constantly fighting against, which basically boils down to 4 fundamental types of misalignment. First, we have vertical offset, where one shaft is simply sitting higher than the other. Next is horizontal offset, where one is pushed further to the side. Then we get into angularity. There's vertical angularity, where the shafts meet at an up and down angle, and horizontal angularity, where they meet at a side-to-side angle. The whole objective of this alignment process is to correct all 4 of these deviations simultaneously to achieve one perfectly straight, continuous centerline.
Section 3. The Alignment Toolkit.
So you might be wondering, how exactly do mechanics fix these microscopic angular and offset deviations? Because you definitely can't just eyeball it. The industry generally relies on 2 primary methods, and comparing them is pretty fascinating. On one hand, we have the traditional dial gauge. This is a classic mechanical tool that measures microscopic variations, but, it is highly dependent on the raw skill, experience, and the mental math of the operator. On the other hand, we have modern laser alignment. This system shoots highly precise laser beams between the shafts and uses a digital display to guide the mechanic. It makes the whole process much more accurate and way less reliant on human error.
But here's the thing. Whether you're using a high-tech laser setup or a classic dial gauge, the core principle is exactly the same. The measuring tools are firmly fixed to the shafts. Then, the mechanics manually rotate those shafts a full 360 degrees. By measuring the gap as the shafts turn in a complete circle, they can map out exactly how far and in which direction the center lines deviate.
Now, what's really wild is how physical the solution is once that measurement is taken. It's a very hands-on fix for a microscopic data problem. To fix a vertical misalignment, mechanics actually slide incredibly thin sheets of metal, called shim plates, right under the feet of the motor to raise it up. To fix a horizontal misalignment, they turn jack bolts. These are heavy-duty bolts positioned on the sides of the equipment base, and turning them literally pushes the heavy motor millimeter by millimeter to the left or right.
Section 4. Phase 2. DBSE check. Okay, so the shafts are perfectly in line. You'd think the job is done, right? Well, not quite. Now we have to look at the space between the machines, which brings us to a supercritical acronym, DBSE. For those new to this, DBSE simply stands for distance between shaft end. It is the exact, physical, horizontal gap left between the end of the pump shaft and the end of the motor shaft. Now, this gap is definitely not random. On the engineering drawing, the specific DBSE is strictly calculated and mandated by the designers. And this distance must perfectly match that drawing in real life. Why? Because later down the line, a very specific mechanical coupling piece has to bridge this exact gap to connect the motor to the pump. If the DBSE is even slightly off, that final coupling just won't fit, and the machines won't be able to turn together.
Out in the field, getting this right requires some incredibly careful physical measurement. Workers use specialized calipers and gauges to measure this gap down to fractions of a millimeter. And if the real-world distance differs from the engineering drawing, well, they have to go back to those horizontal jack bolts we talked about earlier and carefully slide the massive motor forward or backward until the DBSE is absolutely flawless.
Section 5, Phase 3, Soft Foot.
All right, so the center lines match and the distance between the shafts is perfect. Now we reach the final technical check to ensure the motor is truly firmly planted on the ground. This phase asks a really vital question. Is the motor actually stable, resting naturally on all four of its base feet, or is it just being forced down under the extreme tension of the heavy anchor bolts? Think of it like a wobbly restaurant table. If you just force a heavy weight down on the short leg of a table, you'll end up bending the whole table frame. In a motor, this hidden structural tension is called a soft foot, and trust me, it will cause massive, destructive vibrations the second that machine is turned on.
Let's look at how they detect this, because it's a very clever little physical test. Step 1. The mechanic tightly secures all 4 bolts on the motor's feet. Step 2. They attach a highly sensitive dial gauge to just 1 foot. Step 3. They completely loosen the bolt on that single foot. And Step 4. They watch the dial gauge. If the foot suddenly springs upward when unbolted, boom, it means the motor was under unnatural stress. That is a soft foot. To fix it, they have to slide in more of those paper-thin shim plates to fill the invisible gap, so the motor sits totally relaxed and perfectly flat.
Section 6. The millwrights' expertise. Balancing all of these factors, the shaft offset, the DBC gap, the soft foot, is an absolutely incredible juggling act. And this brings us to the human element behind all this precise data. Our source material gives us this wonderfully blunt quote about the reality of the field. It says, "If an unskilled mechanic performs the alignment, fixing one side ruins the other. They might spend all day on just 1 or 2 pumps." It just perfectly highlights how incredibly sensitive and honestly frustrating this microscopic balancing act can be. You fix the vertical height with a shim, but oops, you accidentally ruin the horizontal angularity. You fix the angularity and suddenly your DBC gap is messed up. It's just an endless loop if you don't have the right experience.
So, the crucial takeaway here is that your standard construction workers are not the ones doing this job. Construction companies actually bring in a specialized, highly skilled master mechanic known as a millwright specifically for this phase. When those massive pumps arrive and are set on their foundations, the millwright steps in. It's their unique intuition, patience, and spatial awareness that literally turns a chaotic, vibrating piece of metal into a perfectly humming powerhouse.
It really kind of changes how you look at the industrial world around us, doesn't it? The next time you see a massive pump or motor running completely silently, seemingly without any effort at all, ask yourself, who spent hours out there with shims, lasers, and jack bolts to achieve that perfect centerline? It is a hidden, highly skilled human effort that literally keeps our industrial world spinning smoothly without vibrating to pieces. Thank you so much for joining me on this explainer today, and remember to keep asking the big questions about how things work.